Okay, so I think it is time to start. Today we celebrate the World Logic Day, which was actually yesterday on January 14th. And the World Logic Day was proclaimed by UNESCO 5 years ago, and the date was chosen because it is the date of death of Kurt Gödel and the date of birth of Alfred Tarski. And here we have our fourth event in our series, which is organized jointly by Nazarbayev University, Astana, Kazakhstan, and Mathematical Center in Akademgorodok, Novosibirsk, Russia. So today we have three talks, and here's our first speaker, Junle Goh from National University of Singapore. Okay, Junle, please.
Thank you, Nikolai, and thank you, Manat, as well, for both of you, right, for organizing this event and inviting me. I'm very happy to speak here. This talk is a little bit of a survey talk, so it'll be mostly results of other people, but also some results of myself and other people. But at the end, there'll be a couple of new results or maybe observations that I think are interesting. So let me start with a review of what the Virac lattice is about, right? And I won't if you have never heard of the Virac lattice, I don't think you will learn much about it, but at least hopefully I'll give you the big ideas. So the goal of this pursuit, right, is to classify the computational content of mathematical theorems. And so the way we go about this is a two-step process. First, right, we take a mathematical statement of interest, right? For example, think of something like a for all there exists kind of statement. And we formalize these as multi-valued functions. Okay, so the input, right, what we call an instance, is like the like sort of corresponding to the for all part, right? And then we say there exists some solution to it, right? And there's the exists part. And of course, there might be multiple solutions, which is why we say it's multi-value. But also, what is this represented space thing? So I won't define it formally, but the idea is that things we deal with in mathematics, right? There are a lot of data types that we deal with, right? Not just the set of natural numbers or set of elements of Cantor space or Baire space, right? There are a lot of data types out there, but using represented spaces, we can essentially study them by studying things that happen on Baire space or Cantor space. Okay, so this is, I've skipped a lot of details here, right? But this is something that we can do, right, for a lot of interesting problems. And then we want to compare these problems using a notion of reduction, which for this talk, we'll focus on the notion of Virac reducibility or uniform reducibility, as it is sometimes called. Roughly speaking, we say that a problem F is Virac reducible to a problem G if there is some uniformly computable procedure for solving F. Okay, and this procedure has to query G exactly once. Okay, so let me give you an example just to show you what I mean. So here is a picture of a Virac reduction. Okay, on the left column, we have the problem, which is you're given some function from n to n. This is the p on the slide. We're given some function from n to n, and we are assuming that it is not onto. Okay, so this is just an assumption that is, it's not given with any evidence, okay, but it's just something that we assume is true of the given p. And then our job is to find a witness to this fact, right? So we want to find something which is not in the range of this given p. Okay, so well, you can probably convince yourself that this cannot be done computably, right? There is no algorithm that will take in such a p, right, and always produce something that's not in the range. However, we can do this computably if we have, well, sort of oracle access to the pigeonhole principle. And that's the second column in the picture, where you can see that on the top right, I have defined a coloring. Okay, so this is a function from n to n, which has a finite range. Okay, and then if you apply the pigeonhole principle, right, you get some infinite monochromatic set for that coloring. And we see that, okay, if we start from this P, right, and then we define this coloring C, first of all, the function that sends P to C, right, is computable, right? And now if you think about how does this capital X look like? Well, this coloring has a very simple form. It's like you have, at first it starts out as like, let's say color 0, okay, and it goes for color 0 for a bit, and then it switches to color 1, and maybe it does that for a bit, and eventually it stabilizes on a single color, and it does that forever. Okay, so that's a very simple coloring. And so if you have an infinite monochromatic set for this coloring, then you can just look at its color, right? The color, the eventual color, that is going to be a number which is not in the range of P, right? Essentially, the coloring C is kind of guessing what is the minimum solution to P, right? And pigeonhole helps us guess correctly, essentially. So the key things to note here is that the transformation, right, from P to C, that's a computable process. Also, the transformation from this capital X to the color of capital X, right? That's also computable. Well, it's computable using the coloring itself, right? And more generally, we will allow ourselves access to the original instance when we perform this computation. Okay, so it might not be straight up computable, right? But it must be computable given access to the original instance as well as the solution that you are given. Okay, so this is the idea, right, behind Weierach reducibility, right? We have this, again, to recap, there's an algorithm that goes from instances of F to instances of G, and also from solutions of G to instances of F, but this second one can use the original instance of F. All right, so that's the kind of general scheme of things. Now, as usual in recursion theory, right, if we have some kind of structure like this, we can look at the degree structure, right? We take the quotient, right, by this notion of reduction, and we see, well, what are the properties, right, of the ensuing structure. So here are some features of the Weierach degrees, right, which is the quotient structure where you say that, okay, two problems are Weierach equivalent, right, if they are reducible to each other. The first point is that this degree structure is very rich. So the Medvedev degrees embed, for example. And this means that, well, at least all of the usual degree structures that we study, right, all of them embed as well. Okay, so there's a lot of stuff in here, right? And in terms of cardinality, it's also big. The second point here is that there are many natural algebraic operations between, on this degree structure. So for one, it is a lattice. So you have a join and a meet, right? But you also have other natural things that you can do, right, to these problems. For example, we have the parallel product. So that's a binary operation where you take two problems, and then you want to consider a problem where you just have to solve those two in parallel. So you're given an instance of the first one and also an instance of the second one, and you want to solve each of them. You can also talk about the compositional product, right, which is trickier to define, but it captures the idea of using one problem and then using the output that you get, right, to consider perhaps a second problem, and then sort of using problems in series instead of in parallel. So these are all, and there are many others. So there are several operations that we can consider which are of interest. The third feature is that we have many benchmark problems. So on the slide, I've listed a few, right? For example, we have the identity, right? That's a simple problem. We have this choice on natural numbers. That's the second line. That one we saw on the first slide, right? So that's the problem of if you're given some function which is not onto from naturals to naturals, find something that's not in the range. And then we also have other examples which are familiar to people well, we could either do recursion theory or reverse math, right? Weak Koenig's lemma, weak Koenig's lemma, things like that. And let me just skip to the last one here, right? So last one is a fairly strong problem. We have an infinite tree in n to the less than n, right? Sorry, I forgot to, yeah, I should have put infinite. I should have put ill-founded, right? That's the correct definition. If I give you an ill-founded tree in n to the less than n, you have to find me an infinite path through that tree. Yeah, so that's the problem, which is choice on bare space, and it is much stronger than the other problems that are listed. So in general, what we like to do is, okay, we want to take some problem that comes from various parts of math, right? It could be analysis, could be algebra, and it could be combinatorics, right? And then we want to compare it to one of these benchmark problems and see how they compare. Okay, now the title of this talk is about interior operators in the Weierach lattice, right? So I've told you about the Weierach lattice. Now let me just remind you what interior operators are, and I'll give you some examples of such operators. First is the definition, right, of a closure operator and also an interior operator. So if you have any partial order, right, then you can make sense of what is a closure operator on it. Well, first it has to be kind of, like f is always less than or equals to the closure of f, right? And second is that it has to be monotone with respect to the partial order. And finally, it's idempotent, right? So if you apply the closure twice, right, it's the same as if you applied once. Dually, you can consider interior operators as well. So basically just reverse all of the inequalities. And in effect, you can just reverse the first one, right? So interior operators will bring you down instead of closure operators, which push you up. And as an example, if you take a topological space and you order the power set of the base space by set inclusion, right? Then the usual topological closure is a closure operator, and likewise for the interior. But in this talk, right, we're going to be looking at closure operators and interior operators in the Weierach lattice, right? So now the partial order is Weierach reducibility. But let me just say a bit about why we care about such things. Right? Of course, I mean I think any kind of algebraic thing is inherently of interest, right? But specifically, what can we use it for? So the idea is that, okay, let's say we have some problem f, right, that we hope to understand. Then if we can compute, right, C of f, okay, where C is, let's say, some closure operator or some interior operator, well, then ideally C of f will be sort of more well-behaved than f, right? Because C of f actually has this closure property, right? If you try to take the closure of C of f, it remains fixed, right? So that's one way in which we can make sense of f. And it also helps us to separate different problems. So let's say if we compute C of f and we compute C of g, right, of some other problem g, and we see that, oh, okay, well, C of f isn't below C of g. Well, then f cannot be below g, right? So that's one way of separating problems. And what I just said applies equally to interior operators as well. Okay, so what are some examples of such operators in the Weierach lattice? Most of the talk is focused on interior operators, right? So I'll give you a few closure operators on this slide. First, we have countable parallelization. So previously I mentioned the parallel product, right? Where you have like two problems, I give you an instance of each of them, and you have to solve both. The parallelization is of a single problem, and the difference is now I give you a countable sequence, right, of instances of this single problem, and you have to solve each of those. Okay, so this I think is I hope you agree that it's a very natural definition, right? given any problem, we can look at its parallelization and see how complicated it is. We can also look at the finite parallelization. So this is a variant where we are only, so we have to declare, right, how many instances we want you to solve, right? And then you just have to solve those, right? But we could give you any finite number and you have to be able to solve that. There's also the diamond, which I won't explain here, but it's basically the analog of the compositional product, but iterated as many times as you want. And more recently, Soda and Valenti have also come up with this unbounded finite parallelization, where kind of it's like stronger than finite parallelization, where the bound on how many instances you give, right, is not kind of declared at the outset, right, but it's only sort of derived from the solution in a computable way. Okay, but yeah, that would be a content of a whole talk in itself. So I won't go into details except that I just want to say there's a bunch of closure operators we know, and these are fairly naturally derived, right, from the basic algebraic operations that we already mentioned, right, like parallel product and also compositional product, right? All of these kind of ultimately stem from those. For interior operators, it's I think it's less well studied. Okay, we still know quite a few examples, as I will show you in this talk, but I think to come up with an interior operator is slightly less intuitive. So I'll give you, I think in total I'll give you 5 classes of examples here. So let's start with the first one. So this is what Brodka calls the upper Turing cone version of a problem. But of course, this idea has existed in some form long before that. So the idea is, okay, I give you a problem F, right? And now this is an interior operator. So I want to produce a problem that's weaker than F, or, like it's less than or equals to F. So what I'll do is I'll keep the instances the same, okay, but I'm going to expand the solution set by saying that, okay, you don't have to produce exactly a solution to F, right? You just have to produce something which computes a solution to F. Okay, so I'm expanding the solution set here. And therefore you get a problem which is easier, right? It might not be strictly easier, but at least if you can solve F, well, certainly you can solve this upper Turing function. Okay, so this idea is also, you can imagine other variants of this as well, right? But this is the one specifically that Brodka looked at. And I just gave some examples at the bottom. Let's say F is weak Koenig's lemma. So that's like I give you an infinite binary tree, right? Ask you to find an infinite path. Well, what is the upper Turing cone version of that? That's finding a PA degree, right? From recursion theory. And here's in the third row, right? Here's a definition that will come up again later. So if your F, right, is what we call computably true. So what I mean is that for any instance of F, there is a solution to that instance, which is computable in that instance. Okay, so that's what we mean by computably true. The notation is kind of borrowed from reverse math, where we're thinking of the problem as the corresponding theorem being true in the standard model of recursive sets. But anyway, if you have such an F, right, which is computably true, then the upper Turing cone version of F, well, it's going to be less than or equals to identity, right? Because any real, right, is going to compute some F solution, right, to the instance that you're looking at. So yeah, so sorry, no, I don't mean any real here. I just mean any real that computes P. Yeah. So yeah. Okay, so this here's one way that you can get an interior operator. Basically, what we're doing is we take the solution set, we apply a closure operator to it, right? In this case, we are doing the Turing upward closure. closely related to this is the stashing operator. This was also defined by Bradka in the same paper, in fact. And what Bradka did is to dualize an existing closure operator. So a couple of slides ago, I told you about the closure operator of parallelization, which symbolically I've written down here. Again, we're given countably many instances of F, and you have to solve each one of them. The dual operation is what we call stashing. Okay, so now, again, we're given a countable sequence of instances of F. Okay, but you don't have to solve all of them. You just have to solve at least one of them. Okay, and also you don't have to say in advance which one you're solving. Okay, and also there's the fine print, which is this sort of vertical bar over the space Y. So the fine print basically means that actually in all but one component, your output is not really it doesn't have to be total in some sense, right? So you don't actually have to produce an element of the output space Y, right? You can just basically refuse to produce any output. That's okay, as long as it's in a single column, you produce some correct output. So that is a technical detail, but it's an important technical detail, but I will not dwell on it here. The idea is basically, instead of solving every instance, you just solve at least one. Right. So okay, this guy, well, this gives an interior operator, and that's not trivial. So that was proved by Bradka. So let me, on the next slide, right, let me give you some examples of this stashing. Okay, so on the top, I've just repeated the definition of stashing. And in the table, we have a few examples. So there are 4 columns in this table, right? Several of the problems, I didn't tell you what they are, right? But let's just see that, okay, in the first 2 columns, we have 2 problems called choice on 2 elements and LPO. Both of them stashed to this single problem called dis. So this is what is called the discontinuity problem. In the third and fourth column, right, we have the parallelization, right? So the third column is the parallelization of the second. And then we see that, okay, when we stash these guys, so when we stash weak Koenig's lemma, right, we get PA, for example. And when we stash lim, right, we get the problem of just producing a set which computes the jump of the input. So if you've paid attention in the previous slide, well, not the previous slide, but the one on the upper Turing cone version, then you see that, oh, okay, this is somehow doing the same thing, at least on certain problems, right? And that's not a coincidence. So Bradka showed that if you have any parallelization, actually stashing is just the same thing as doing the upper Turing cone version of the thing. Okay, so in that case, I would say, it's sort of completely understood. However, if F is not a parallelization, then actually few examples have been characterized. So notice I'm not saying, when I say characterized, I actually do mean that, right? So we certainly have examples of problems F, which do not stash to this discontinuity problem. But all we know is that, okay, they stash to something else, right? But we don't have an exact expression that says, oh, this is the stashing of this guy. Okay, so we don't have a characterization. Of course, we know that there are many other examples, but we don't have a nice theorem that says, oh, okay, this, or a nice formula, right? That says, okay, this stashing is this. Yeah. So I think there's a lot of room for more study here, especially to see if how this interacts with other operators on the Dirac lattice. And if you look in the paper by Bradka, you'll see that he's already done a bunch of very interesting things. Okay, so that's the second type of interior operator that I wanted to introduce, right? We're taking an existing closure operator and dualizing it. I don't know of any systematic way to do this, right? So Brodka did it for parallelization, but I have no idea if it can be done, right, for the other closure operators. Right, so the third kind is, this is somewhat more complicated way to derive an interior operator from an existing operation. So we're taking the residual, and this is in the sense of lattice theory. So recall this compositional product, which I waved my hands about just now, right? Basically, if you have problems H and G, then H star G is, it captures the strength of being able to apply H and then, no, sorry, apply G and then apply H. Okay, then this operation, Brodka and Pauly showed that it admits a right co-residual. Okay, so what that means is the equation on the slide. Namely, let's say we have some H and some F, right? And you think, okay, what are the G's so that F is below H star G? Turns out that this set, the set of all such G's, has a minimum in the Weierach degrees. And that's a theorem, right? So that is not obvious at all, right? In general, there's no reason to believe that minima exist, right? But in this case, they show that it does exist. So that's quite remarkable. And they also show that actually, if you take, let's say you take the left co-residual or you take the right residual, none of those exist. Only this one exists, right? Okay, so let's look at this operation here. Well, first of all, H implies F, right? Certainly it's below F, right? Because if you put F in the right-hand side here, right, then F is certainly below H or F. Okay, that's a basic property of the compositional product. And also this operation is monotone, right? So if F0 is below F1, right, then H implies F0 is below H implies F1. All right, so this you can see if you just write down the definitions and do some algebra. Now, is this an interior operator? Well, almost. So at least, right, what can be said is if H is closed under compositional product, okay, so if H star H is equivalent to H, then you can work the algebra and you can see that this operator becomes an interior operator. In other words, H implies F. It would be the same as H implies F, provided H satisfies this closure assumption. Okay, so here's another interior operator that one could look at, right? In some sense, we are kind of like quotienting by H in some sense. That being said, well, once again, examples are tricky to come by, so I'll show you some examples on the next slide. Okay, so on the top is the definition of the implication again. And then I've listed several problems which are known to be closed under composition. Okay, and these is due to these various authors. And I include this list just to show you that we are still figuring things out, right? So you can see here that there are two papers from last year. So some of these were not established until very recently. But okay, the results below were slightly older, and most of them involve this choice on natural numbers or some variation of it. There are other results involving the implication, which I didn't list. But I just want to focus on these. So you can see that, okay, if you take weak Koenig's lemma, right, and then you take some jump of Cn. So I didn't tell you what the jump is, but it is another algebraic operation. If you take some jump of Cn, right, and you say, okay, take jump of Cn implies weak Koenig's lemma, you get PA. Okay, and interestingly, this is still open for whether it's true for Cn itself. If you take weak Koenig's lemma and you take Cn implies that, well, then you get Martin-Löf random, right? So that's the problem of producing a relative Martin-Löf random. And essentially, this second point is mostly related to the result of Kuchera. It's about the tails of Martin-Löf random. And again, along similar lines, if we take RT22, so Ramsey's theorem for pairs, right, and we take Cn implies it, well, that is RT22, but with finite error. So we are saying, okay, instead of asking for an infinite homogeneous set, we just ask for an infinite set, which is homogeneous mod finite. So there's some fudging there, right? And so this becomes a slightly weaker problem than RT22 itself. Okay, so these, again, like I said, there are a few other examples known, but in general, I think this is also not very well studied, just because it's very hard to find kind of, to characterize, right, implications between natural problems. Like if I just choose two problems randomly, and I ask, okay, what is like H implies F, right, for those two, you know, in general, we don't know, we don't have nice answers for this. So yeah. Okay, so that's the third kind where, you know, we had this, you know, the stars aligned, right, and we had this operator which emits a right co-residual, and then you can use it to do stuff. The next two, so remember I said 5 classes, so we've done 3 out of 5. The next two is really kind of the focus of my talk, right? So the first one here is we're taking the maximum of, so we're given some F, okay? Fix a problem F. Look at all of the problems G that are below F, but with a restricted codomain. Okay, so for example, you could fix a codomain X, right? And you say, okay, look at all of the problems G below F which have codomain X. So for some choices of X, this max exists. Okay? And this was proved, for example, for the X being the natural numbers. This was proved by Zafarov, Solomon, and Yokoyama. And this is what we call the first order part of a problem. Okay, so let me just restate the definition again, right? For this special case, if I give you an F, and if I look at all of the G with codomain N, which is below F, those G's have a max, and that max is what we call the first order part. Okay, and this idea, right, even though it was first expressed by Zafarov, Solomon, and Yokoyama, right, this idea of looking at this max has been around for a while, right, from the very beginnings of at least the recent wave of study in this area. So way back in 2012, right, we already knew that the first order part of lim, right, is choice on natural numbers, right, by Bradka, Garadi, and Marcona. And yeah, so in the next few rows, I list several other known examples. Let me just mention the last row here. So this is joint work with Arno Pauli and Manlio Valenti. A couple of years ago, we showed that if you take this problem, ds, that is the problem of given an infinite ill-founded linear order, find an infinite descending sequence. Okay. So we studied the Weyrach degree of that problem, right? And part of our study involved showing that the first order part is this problem, which we call pi11 bound. So it's you have a finite pi11 set, and you want to find a number that bounds it. Okay, these are sets of numbers. So I give you a code for a finite pi11 set, and you have to give me a bound. Okay, so that's one quite I think quite a prevalent example of this interior operator, the first order part. Let me also mention that you could also do this for any fixed finite number. So this, again, this idea has been around for a while, but I think the first place where it is explicitly stated is in Cipriani and Pauli, where they call this the K part. Now, my question here is, well, okay, so we know that this max exists if we take the space X to be natural numbers, and also for finite K, right? My question is, okay, which other spaces X is this defined or useful? Right. Of course. So there are some trivial answers to this question, right? So in general, it's an open-ended question, but I think it will be interesting to people who are experts in computable topology, right? Because there are lots of spaces out there which might give interesting answers. Okay, so this idea, right, on the idea that's on this slide, is going to come back again. But right now, let me tell you about the final class of interior operators. It's what we call the deterministic part. So this appeared explicitly in joint work with Pauli and Valenti, where we say, okay, now look at all of the G that's below F, but now we're not, we're focused on only the single value G. And we say that, okay, G has codomain Baire space. Okay, so this max also exists. Okay, that's what we proved in that paper. And once again, this is an interior operator. And here are some examples. Okay, so again, way back in 2009, right, Goradi and Marcona already showed that the first order part of weak-Koenig's lemma, no, sorry, not the first order part, the deterministic part of weak-Koenig's lemma is identity, right? And this expresses the, I think the well-known intuition, right? That, okay, if I just give you an arbitrary path, right, in an ill-founded binary tree, right, you cannot uniformly get things out of it. Right? So this is the concrete way to express that idea. And over the years, yeah, there have also been a few other examples. For example, by Kihara, Marcona, and Pauli, they studied the Weyrach degree of, if I give you a countable closed subset of Cantor space, and your job is to list them out in a sequence, right? So I'm giving you them, I'm giving you this countable closed subset as coded, right? And your job is to actually list them. So that problem, they show that the deterministic part is lim, which interestingly, this descending sequence problem that I mentioned earlier, that first deterministic part is also lim. But what's interesting here is to compare the third row and the fourth row. So in the third row, we have choice on Baire space, which is, if I give you an ill-founded subtree of n to the less than n, find an infinite path, right? So from a naive point of view, this sounds very similar, right, to the descending sequence problem in a sense that you can have a computable tree with no hyperarithmetic path, ill-founded. You can also have a computable linear order, right, with no hyperarithmetic descending sequence. Again, you found it. So even though from that perspective, they are the same, right? But from the uniform perspective, there's a huge difference, right? This problem you see on Baire space, that corresponds to finding the path on a tree which has a unique path, right? And so that's a fairly strong problem, certainly much stronger than just computing, one Turing jump, which is what lim corresponds to. So the point of this result is that by computing the deterministic part of DS, we can illustrate why this choice on Baire space is separate from this descending sequence problem. Now, here's some notation that we'll use in the rest of the talk. So note that being single value is not a degree theoretic property, right? So even if you are single value, you will be Weyrach equivalent to stuff which is not single value. So we say that F is deterministic if it is equivalent to some single value problem with codomain Baire space. Okay, so I think this kind of concludes the survey part of my talk. Now I'd like to move to some, well, at least I'd like to set up some material to state the new result that we have. So here is something else that also appeared in this paper with Pauli and Valenti, So this deterministic part actually, it works just for other spaces as well, not just bare space. Okay, we can take any represented space and we can say, oh, okay, look at all of the single valued problems below which have that codomain. Okay, so, and in particular, I'll just look at the case where this X here is the natural numbers. Okay, so that gives us another interior operator. And in that paper, again, we showed that actually this, in some sense, it doesn't give us something new. Okay, so if you take all of the single value guys with codomain n, which are below you, and then you take the max, well, that's actually the same as, oh, first you take the deterministic part, and then you take the first order part of it. Okay, so we've composed two interior operators, and then we get this this guy, this deterministic part restricted to n. Okay, so first of all, these two guys are the same, right? That's the first half of the proposition, but also there is this relationship, right? That these guys is always less than the deterministic part of the first order part. Okay, so okay, right now this looks like some, just like some algebraic fact, right? But the fact that this relationship exists, right, it causes a collapse in the sense that, well, first of all, if you take the first order part of the deterministic part, this is an interior operator. And in fact, right, this is actually equivalent to all of these guys. Okay, so after you have first order of deterministic, if you tag on more like first order or you tag on more deterministic, it doesn't actually change the Weierach degree. And the reason why we have this collapse is precisely because of the proposition. However, this raises the obvious question that, okay, in the proposition, we have this inequality. And in the paper, we posed the question about whether this inequality can be up. So we did not, in fact, have any examples where, where in all the examples that we looked at, right, you actually just have equality in the whole thing. So we asked if, oh, okay, is it possible for them to be separate? And in the rest of the talk, I'd like to say a few words about this, right? So we have ongoing work now that says that, okay, the answer is no, but I think the result itself is maybe less interesting than the observation that we made on the way to proving the result. So I'd like to tell you about that as well. All right, so the question on the previous slide is now restated in the title. And there's an equivalent form, which I think is easier to understand and also I think easier to think about. So equivalently, we can ask, is there a first order problem F such that the deterministic part of F is not first order? Okay, and by the way, here, when we say first order, we mean it's equivalent to some problem with codomain M. Okay, so this is actually equivalent to the original question. And let's think about, what such a problem would satisfy, right? So we're trying to find such a thing, right? But let's think about, okay, what if it did exist, right? What properties does it have? So let's say we have such an F. Okay, F is first order, deterministic part of F is not first order. And let's first look at the deterministic part of F, which I'll call G. Okay, now G is below F, right? And F is first order. So that tells us that G must be computably true. Okay, because, well, why is that? Well, think about the Weierach reduction, right? The Weierach reduction, well, first it takes an instance of G, and then it computes an instance of F, all right? And now to go backwards, it has to say, well, given any solution for F, right, to that F instance that it computed, it has to compute then a solution for G, right, together with the original G instance. So certainly whatever solution you compute, right, because the solution you are given, the F solution, is just a number, right? So whatever G solution you're computing, right, it's computable in the original G instance. And so that's exactly what it means for G to be computably true. And this is a general fact, right? Whenever you have something that's below a first order problem, you must be computably true. This was already stated in the Zafarov-Solomon-Yokoyama paper. Now, this is kind of a picture that summarizes the properties that we are now looking for. Okay, so we have this G here, which is secretly deterministic part of F, and then G is below F. And these are the properties that they have, right? G is single valued because it's the deterministic part of something. It's not first order. Okay, that is what that's what's written on the top, right? And also we now know that it must be computably true, right? Because it's below F. And as for F, well, F is not single valued and it's first order. And also in between, right? In between G and F, so except for G itself, you cannot have any single valued thing. This in-between thing is expressing the fact that, well, at least it's a partial expression of the fact that G is the deterministic part of F, right? Because remember, deterministic part of F is the max of all the single valued things below, right? So if there was something single valued in here, in between, then G cannot be the deterministic part. Okay, so we're looking for such a thing, right? We're looking for G and F, right, with these properties. And so what we had in mind was, okay, well, let's say we fix G, right? And then we let F vary. The sort of the optimization that we want to do here, right, is that we want F to be kind of as close to G as possible, right? Because we want to have no single value thing in between G and F. So, right, it would make sense for F to be as close to G as possible. And furthermore, we need F to be first order, right? And so this led us to the following observation, which is okay. So I'll say what I okay. First of all, right, Zafarov, Solomon, and Yokoyama showed that every problem which is computably true is below some first order problem. Okay, so in fact, you can characterize the computably true problems as the ones which are below some first order problem. Now, in their proof, they defined this problem below. Okay, so this is this thing that I call G1. Okay, and our observation is that actually this G1 is the least thing that's above G, which is first order. Okay, so G is computably true, okay, and it may or may not be first order. But if you look at all of the first order things above G, those have a minimum. And that minimum is precisely this G1 over here. Okay, and so again, G1 already appears in the proof by Zafarov, Solomon, and Yokoyama, right? But the observation that it is actually the minimum, right? This is, I think, something that is worth pointing out. And now with this, okay, with this theorem, we have kind of a path to answering the question on the previous slide. Why is that? Well, here's a corollary of the theorem. Suppose G is computably true, okay, and it's single valued with codomain bare space, and that G1, okay, so G1 is the one defined here, G1 is not deterministic, okay, then deterministic part of G1 is not first order. Okay, so let me explain why this follows from the theorem above. So first of all, well, it's easy to see that G is below G1, right? This is, I mean, this is part of the theorem, but also you can see it for yourself if you think about it, right? G is below G1, and also G is single value with codomain bare space. So G must be, in fact, below the deterministic part of G1, right? That's the definition of the deterministic part. And now, okay, we assume that G1 is not deterministic, right? So therefore, this reduction is actually strict here. Okay, now, so we have this first sequence of reductions. To finish the proof, maybe it's best to think by contradiction. So let's see what happened, right? If deterministic part of G1 was actually first order. Okay, so this guy in the middle, what if it's first order? Well, look at the theorem, right? The theorem is saying that the G1 is the minimum thing above G, which is first order. Okay. So, well, this is, yeah, that's just not going to happen, right? So that's the proof of the corollary. And now with this idea, right, now we can quite easily construct some problems with these properties. So I'll vaguely describe how on this slide, right? So this is the corollary, but repeated. And now the idea is, okay, we're going to construct a sequence of computable reals, which we think of as a single valued function from n to vector space, right? And we construct these, right, using diagonalization to ensure that this G1 is not deterministic. Okay, so I'm not giving the details, but this is a diagonalization. There's no conflict or anything. So then the result is that, okay, G1 is first order, right? Well, G1 has codomain n, right? But deterministic part of G1 is not, because we have ensured the assumptions of the corollary. Okay, so this is how we answered that question. But yeah, I think what is maybe most interesting here is the this observation about the first order closure, right? So every problem which is computably true has a least first order problem above it, and I think that's a nice thing to know. That's all that I have for my talk. So thank you for your attention, and I'll just show the references that we have for a brief moment. And yeah.
We thank you. So let's thank the speaker. Are there any questions? So if you have a question, please just unmute yourself and ask a question. So maybe I will ask a question. Could you please show slide 12?
Okay.
Thank you. Maybe this is a stupid question, but is it also true for strong Weierach reductions, this proposition, or in general, no?
Well, okay. I'm not sure. I think maybe part of it would be true, but yeah, off the top of my head, I couldn't tell you unless I look at the proof again. The thing is that for example, the first order part, right, is defined like kind of up to Weierach degree. So it's not, if I remember correctly, it's not a strong Weierach first order part. Yeah. So that means that whenever you talk about these notions in strong Weierach, that means you're talking about the specific problems rather than the degrees, and so it becomes kind of less meaningful, right? Because you can't exploit them to reason about the degrees.
Okay, thank you. So are there some other questions? So if there are no further questions, then let's thank the speaker again.
Thank you.
And now we have 7 minutes break.
Okay, so thank you everyone. The last talk for today's workshop is given by Dino Rossegger from the Technische University of Wien. So Dino, please, stage is yours.
Thank you, Manat, and thank you also, Nikolai, for organizing this workshop. It's the first time I'm speaking on World Logic Day, so it's quite an honor. I'm talking about a joint project which is still going on in the sense that I hope to upload the paper on arXiv sometime by the end of the week, although I don't want to make too many promises. And it also has a growing list of co-authors. As I saw in the abstract, I wrote that it's joint work with Uri Andrews and Steffen Lemp. In the meantime, we've added David Gonzalez and Hong Yu Tzu. David is a PhD student at Berkeley, and Hong Yu is a PhD student at the University of Wisconsin Madison. And so yeah, the title of my talk is The Borel Complexity of Models of Finitary First Order Theories. But it started with like a more modest goal. And I guess I'm going to start by just, I don't know, like talking about my journey to this project. Namely, at some point during the lockdown, I was actually teaching, I think, like a logic course. And at some point in these introductory logic courses, you use compactness to produce all kinds of weird models. So in particular, we were producing non-standard models of arithmetic. And at some point during this, I was wondering like how complicated these models of arithmetic are. Like in some sense, arithmetic is such a strong theory that you would expect that like if you have a non-standard model, then that non-standard model must be structurally very complex. And I asked, I think it was in 2020, like fall of 2020, on Math Overflow, this question in essence: how complicated is the set of countable models of true arithmetic? And it has been, for 2 years, I think nobody posted an answer to this. So let me quickly say what I mean by true arithmetic, which is so that we're all on the same page. So true arithmetic, denoted as TA, is just the first order theory of the discrete semmering of the natural numbers. So maybe possibly the best studied theory in math. And as we all know, true arithmetic is quite complicated. I mean, there's many theorems that like somehow tell you, okay, like true arithmetic is a complicated theory. So we have like things like Tarski's undefinability of truth, which comes out of Gödel's incompleteness theorems. We have Tenenbaum's theorem, which tells you that like true arithmetic does not have non-computable non-standard models. The only model of true arithmetic that is computable is our standard guide in natural numbers up here. Then there's other theorems in computability theory, for instance, Solovey's characterizations of the Turing degrees of non-standard models. And also I want to mention something quite recently, which came out of my interest in the complexities, like my work with Antonio Montalban, where we showed that if you look at non-standard models, then they indeed must be structurally quite complicated. They cannot have finite Scott ranks. And now this talk is basically mainly about this question and basically the project that it led to, namely how complicated is the set of countable models of true arithmetic. So we have 2 to the aleph naught, sorry, there's a typo here, many models of true arithmetic. And so what we need, so we cannot really use computability theory to answer these questions. Instead, we have to look into descriptive set theory. And the right measure of complexity to measure the complexity of such a set is Borel complexity. And in some sense, this project is about investigating like if there's any connection at all between first order properties of true arithmetic and basically the descriptive complexity of the set of its countable models. And it, like, I mean, I asked this question here on Math Overflow before I worked before my work with Antonio Montalban. But like after that, I got even more interested in it because what Antonio and I did, we used the least number principle, so basically induction. And the fact that true arithmetic has partial truth predicates. So like there's a formula, like a sigma n formula. There's a formula that for every n tells you about sigma n formulas, whether they're true or not. And for every n, there is such a formula, sorry. And we use these were basically the 2 main ingredients that allowed us to infer that like the Scott ranks can't be finite. And Scott rank basically tells you that the complexity of the isomorphism class of a specific model is so and so hard. So that's how the Scott rank fits into this. And this already suggests that somehow the descriptive complexity of the models should depend on first order properties of true arithmetic, because like, so we use basically these first order things that we have in true arithmetic to show that, okay, like this descriptive complexity of the models cannot be high. So what about like if we look at all the models? So let me set this up. So what am I actually talking here about when I talk about Borel complexity and so on? So I want to reason about all countable models of a theory. So to do that, I need to make this formal, I use Polish spaces. So given a countable relational vocabulary tau, the set of countable tau structures with universe omega, they have a canonical Polish topology. Namely, if we fix an enumeration of the atomic tau formulas and let the atomic diagram of a tau structure be the following string, namely the string dA, where the ith bit in this string is 1, if the ith formula with variables replaced by numbers holds in A and 0 otherwise. So this is now a string in 2 to the omega. And sorry, was there a question? No, okay.
No.
And in fact, like the set of all of these atomic diagrams of structures are a closed subspace of Cantor space, and thus we get an homeomorphism between this set of models in this vocabulary tau and Cantor space, and can define like topological properties as usual. In particular, we can define the Borel hierarchy, which is just for every countable alpha. And every set, we say that X is a sigma 1 set if X is open, X is pi 1 if X is closed, and X is sigma alpha if X is a union of pi less than alpha sets, countable union here. And X is pi alpha if it's a countable intersection of sigma less than alpha sets. There are a few disclaimers here. Well, in order to formalize this first question, I can only talk about relational vocabularies. And as we know, arithmetic is not really a theory that is relational. And I can only talk about countable tau structures with universe omega. But that's not too much of an obstacle, because I can just, instead of looking at the semi-ring, I just look at the version where instead of the addition and multiplication, I have the graph of the two functions. Related to the Borel hierarchy is actually a hierarchy in infinitary logic. So infinitary logic, L omega 1 omega, is basically, it's very much like first order logic, except that it allows countable conjunctions and disjunctions. So, and it admits like this hierarchy here. So for an infinity sentence phi and a countable alpha, we say that phi is sigma 0 or pi 0 if phi is finite and quantifier free. And then we say that phi is sigma alpha if phi is a countable disjunction of pi less than of existentially quantified pi less than alpha formulas. And we say that it's pi alpha if it's a countable conjunctions of universally quantified sigma less than alpha formulas. And so here's a few facts about this. So first of all, okay, every L omega 1 omega formula is equivalent to some formula in this hierarchy. So like this hierarchy really captures all of all that you can express in infinitary logic, L omega 1 omega. And the main theorem that connects L omega 1 omega with like Polish spaces and the Borel hierarchy is the following due to Lopez Escobar, namely that an isomorphism invariant subset of a space of models is Borel if and only if it is definable in L omega 1 omega. So if there is an infinitary sentence that defines it. And there has been quite some work on this theorem, and what in particular gave like a different proof. And if you follow his proof, it actually shows that if you have an isomorphism invariant set X, then X is pi alpha in the Borel hierarchy if and only if it is pi infinitary alpha definable. So we have like this strong connection between the complexity, so like the descriptive complexity, the complexity in the Borel hierarchy of sets, and definability in infinitary logic. And a priori, there is no reason why you would expect that there should be also like some connection with finitary first order logic. However, as we will see, this exists, but a priori not. I mean, here's one example. Consider the class of torsion groups. So this is the class of groups such that, like, after adding elements finitely many times to each other, you will receive packet identity. And here's like a pi2 sentence that axiomatizes this. So for every x, and then here you have like a countable disjunction. So that's a pi2 sentence that's basically satisfied if and only if you're a torsion group. However, a simple compactness argument shows you that you cannot axiomatize the class of torsion groups in first order logic. So we see that infinitary logic has more expressive power than finitary first order logic. And disclaimer, when I say first order in this talk, I always mean finitary, even though that's not quite technically correct. However, if you look at properties which are already first order definable, then it turns out that infinitary logic doesn't gain you very much. So there's an old theorem by Kiesler that says if a finitary first order formula phi is equivalent to some infinitary pi n formula for n a natural number, then there's already a finitary pi n formula theta such that phi is equivalent to theta. So taking the step from finitary first order to infinitary formula doesn't really give me any advantage, and it doesn't let me eliminate alternations of quantifiers. Doesn't really give me any power. And so this theorem was proven by Kiesler. It was actually proven for L infinity omega. So like L infinity omega is like a more general class of formulas where you don't restrict the disjunctions and conjunctions to be countable. And he used like a game theoretic proof. And very recently, Harrison, Traynor, and Kretschmer gave a new proof using forcing. So they forced with elementary extensions. Now, if we come back to true arithmetic, to TA, well, that's a countable set of formulas. Like any first order theory is in a countable language is a countable set of formulas. So you can just take the conjunction over all the formulas in the theory, and you get an infinitary formula, an L omega 1 omega formula. And well, because all of these formulas here just have like finitely many ordinations of quantifier because they're finitary themselves, we get that this formula can be at most pi omega. So it can at most be a pi omega formula and so this implies that if you look at the set of models of a theory, here I just wrote it for true arithmetic, but in general, then the complexity is at most pi omega. It can't be any higher. But we would like to know, I mean, my whole like thought process, or like my whole suspicions are that, right, the set of models of true arithmetic is not simple, that it's complicated. So I would like to show that this bound is actually tight. But how do you show that it's not simpler? And in order to do this, one uses a reducibility called weight reducibility. So and it's defined as follows. So let X be a Polish space and A a subset of X and gamma a point class. So think of gamma as, I don't know, like pi omega, sigma n, something like this. Then we say that A is gamma complete. If for any A is gamma complete if, first of all, okay, A needs to be in gamma. And for every other B in gamma, and here B can be from some other Polish space, B is weight reducible to A, which means that there's a continuous function f from the Polish space Y in which B lives to the Polish space X, to the Polish space X where A lives, such that f of Y is, and here's a typo, f of Y is in A, even only if Y is in B. So that's what it means to be for a set A, for a set B to be weight reducible to A. And then you have that it's complete, gamma, that the set is complete if every other set in the complexity class is reducible to it. Wade showed in 1983 in his PhD thesis that if you take any two subsets of Porter space or like subsets of Baire space, if you want, X and Y, then either X is wedged below Y or Y is wedged below its complement. And you can use this to show that every Borel set has degree either sigma alpha, pi alpha, or like a difference of sigma alpha sets. And yeah, so these D gamma sigma alpha sets are basically just the sets in the difference hierarchy. So it takes difference of sigma alpha sets. And they correspond, like if you take the union over all of them, then they correspond precisely to the intersection of sigma alpha plus 1 and sigma and pi alpha plus 1. So you get like kind of like the delta alpha sets like this. So the wedge degree are nicely behaved. So there's either sigma alpha, pi alpha, and then you have like in between the delta alpha sets, and the delta alpha sets split into like aleph 1 many sets that in the which correspond to the difference hierarchy. So that's it with the setup. Let us look at our theorem, which started as a theorem about true arithmetic, but like got expanded quite a bit. And so this is in essence our main theorem, namely for any first order theory T, and here it doesn't matter anymore, we're not talking about arithmetic anymore. The set of models of T is pi omega complete if and only if T has no axiomatization by first order formulas of bounded quantifier complexity. Here by quantifier complexity, I mean like bounded alternations of quantifiers. And yeah, so there's basically, we don't have any other restriction on T. We don't need T to be complete, and we also don't need T to be in any way related to arithmetic, which was quite surprising to me when we figured this out, that we don't need to use anything about arithmetic, because I was hoping we use something like partial truth predicates to show that, I don't know, back and forth relations are definable or something, but no, none of that is necessary. Let's look a little, okay, well, what does this imply? Well, I mean, and that's, I guess, I don't know why I included the proof, it's quite obvious. Well, if T does not have a bounded first order axiomatization, then the set of models of T is also not definable by an infinitary sentence of finite quantifier complexity. And the proof is just, well, assume it was, then we can use like the aforementioned Lopez-Escobar theorem to get that it's actually sigma n, and thus it cannot be pi omega complete. So it has actually an axiomatization by bounded quantifier complexity then. Okay, let's look a little bit at how this theorem is proven. And when I first asked the question about true arithmetic on math overflow, very quickly, I think it was Ted Slayman said, oh yeah, you're gonna have to use worker constructions, which is like this method to do like iterated priority constructions. And when he said that, and I thought a little bit about it, and I thought that he's probably right. And then I stopped thinking about it for a year or two, because I thought it's probably very hard. And it turns out that indeed you need to do this. But as we will see, the work has already been done for us. Okay, but first let's look at the easy direction of the theorem, namely to show that, so what was the direction, sorry? That if T has no axiomatization by first order formulas of bounded quantifier complexity, then its set is pi omega complete. Well, okay, so say S has a set of sigma n formulas axiomatizing mod T. Well, then we can do the same trick that I explained before. We can just like take this axiomatization and take the conjunction over all the sentences in their axiomatization to get a pi n for n plus 1 formula. And so by Lopez-Escobar, mod T is pi n plus 1. So we just have shown the contrapositive of the backwards direction. So that was easy. And the other direction follows essentially from the following lemma, which I would call basically our core lemma, which is just basically a more technical way to phrase it. So let T be a complete first order theory for which there is a collection of theories Tn such that for every n, t is not equal to tn, but t intersect sigma n is equal to tn sigma n. So the n theory looks at the level sigma n exactly the same as t. If you want, the way I envision this is essentially kind of like you have like here, you have here your theory t, and here you have like the levels, like, and like at every level, like kind of like there's a theory. So here t1 branches off, t2 branches off, t3 branches off, and so on. And well, if this is the case, if we can find such Tn, then the set of models of T is pi omega complete. Indeed, for each pi omega set P, there is a continuous function mapping any P in P to a model of T, and any P not in P to a model satisfying Tn for some n in omega. Notice that this theorem here, this lemma here mentions completeness, while our theorem does not. Well, to remove completeness, we can just take some completion of some incomplete theory T, as long as it's consistent, and use the non-bounded axiomatizability that we already have of T to obtain like these theories Tn. And then we have like just produce in the pi outcome, we produce like models of one completion. In the sigma outcome, we produce like some other guys as usual. So the technical crux of this whole project is actually improving this lemma. And the main issue is to get like this function here continuous. Namely, if you want this function to be Borel, I mean, okay, then you won't get a very interesting result, but then it's quite easy, because then just in a Borel way, we can check whether P is in some pi omega set, and then we can just like build a model of T, as long as T is Borel. T is always going to, anyway. Okay, so how do you prove this lemma? And in order, well, as I mentioned before, it was suggested already like in 2021 that you probably have to use worker constructions. And this is right. At least I don't know if there would be another proof, but thankfully the work has already been done by Solovey when he characterized the Turing degrees of non-standard models of arithmetic. And the version of this theorem here is due to Julia Knight. Namely, Solovey proved the following theorem. Let T be a complete theory, and suppose that R is an enumeration of a Scott set S with functions Tn, which are delta n uniformly in n, such that for each n, the limit of this Tn is an R index for T sigma n, and for all S, T and S is an R index for a subset. Then T has a model representing S with B Turing below X. So there's a lot of new stuff that I haven't talked about in this theorem. So let me just parse it for you. Here. Okay, so first of all, what is a Scott set? If you are a computability theorist, you probably will have heard about it. But a Scott set is a set of infinite binary strings, or like elements of counter space, or like is a set of natural numbers usually. But it's convenient to have it set up like this, as a set of infinite binary strings, such that it is closed under Turing reducibility. So if X is Turing below Y and Y is in S, then X is also in S. It is closed under joins. So if X, Y is in S, then the computable join of X and Y is also in S. And here is what basically makes a Scott set a Scott set, is if X is in S and X codes an infinite binary tree, then S needs to contain a path through T, through this tree. So that's what is yeah, so that's basically what, if you think about it, this is kind of like some compactness property that a Scott set has. Now, I told you what a Scott set is. So what is an enumeration of a Scott set? So a countable Scott set, right? It's like a collection of sets, or collection of strings. But now I want to code it into a single string in order to be able to do some computability theoretic constructions. So I said that R is now an infinite binary string, is an enumeration of a countable Scott set. If you look at R like as a table and you look at the columns, then the columns correspond exactly to my Scott set S. And at last, what does it mean for a countable model M to represent a Scott set S? Well, it represents a Scott set S if for all complete bounded types and every element C in M, the type gamma CX is realized in M, if and only if gamma is in the Scott set, and well, the type should also be consistent with M, with like the set of first order sentences that hold of elements of M. So like if the type is consistent and the type is included in S, then it needs to be realized in M. So that's what it means to be represented in S. And that's also, so this notion of representation is basically what Julia added to Solovey's theorem. Solovey was only talking about models of arithmetic and had a different notion of what it means to be represented. So as I mentioned before, so like no proofs of this use methods for iterated priority constructions, which are like these methods used in computability theory, mainly, I guess, like in computable structure theory, which allow you to do complicated priority constructions as long as some, for high levels, as long as some conditions are met. And the original proof uses this Harrington-style worker argument, which is a very nice way to think about these constructions, but like it's quite hard to write it up. And the version above is due to Julia Knight, who wrote a paper in 1999, where she proved it actually using her alpha systems. Which actually, when I now discovered this paper, when we were working at this, I was quite surprised that she managed to prove it using these systems. I would have thought that they're too weak, but apparently it's possible. Okay, so how do we actually prove this lemma? Well, okay, so there's two parts. And the first part is, well, we actually need to arrive to a theory T that satisfies these things here. And how do we do this? So we're given, okay, so we have a theory T, and we want to show that the set of models of T is pi omega complete. So what do we need to produce? We need to produce the weight for any pi omega set P. We need to produce a weight reduction that reduces P to the set of models of T. So assume we are given like this T, which is not axiomatizable by bounded quantifier formulas, and we are also given this theories Tn, such that Tn intersect sigma n is the same as T intersect sigma n. And we are given also an enumeration of a Scott set S that contains T and Tn. And additionally, we are given a Borel code C for this pi omega set P, which we want to reduce. So for those of you who don't know what a Borel code is, it's basically just the binary tree. It's an infinitely branching tree where basically the leaf nodes are just like codes for the basic open sets, and the internal nodes are either basically take the union of everything that's below me or take the intersection of everything that's below me. So it's a well-founded tree in Beer space, and thus we can code it by real and just like also use it as an oracle for constructions, etc. Okay, and well, since we have a pi omega set, we just might assume that P is given like as the intersection of these Pn sets, which are all sigma n. So how do we prove the lemma? Well, we're given a real X, and we produce indices for these functions Tn. So these are indices for partial computable functions Tn, such that if you feed the partial computable function Tn as an oracle, the n minus first jump of X and S, then it's Rtn plus 1 if X is not in P and S. So P and S here is like, because this is a sigma n set, so it's basically the stage S description of So basically, because it's a sigma n set, you can imagine it as like kind of like it's a CE process. So like if you want to see whether X is in Pn, you have like an approximation PNS. So like at Pn0, it's not in Pn. At Pn1, it's not in Pn. At Pn3, it's not in Pn. But at some point, if it is in Pn, at some point, it's going to get enumerated. And well, okay, so we produce this Tn plus 1 if it's not in PNS, and we produce just like T so if it is in PS. So something I haven't said here, like Rtn plus 1 is just like, right, you have like this enumeration of the Scott set, and there are columns for Tn plus 1 and columns for T, and like Rt is just like the smallest index for these columns of a column that has this. And well, you can manage to do this recursive in, well, okay, you need X, and you need C, the Borel code, and you need like this enumeration of the Scott set SR, plus you need like to know the theory and all these other theories. And annoyingly, you need the jump, because basically the jump of this, because basically what you're testing here is like equality of you have to basically see, okay, well, take the least index of R such that the column of this index is equal to T. So like equality of two sets, you cannot do this computability in a computable way, you need a jump. So that's basically the first step. And that's basically, I guess, our main creative input in this theorem. And the second step is just basically showing that Solovey's theorem is continuous in the sense that, well, okay, we produce all of these theories Tn, and we give you like this R and this T and this Tn and C. You don't even care. So we give you this T, these Tn's, and we give you R and X. And basically, we give you all of the stuff that you need to run Solovey's theorem, and we just have to show that like the step here from the conditions to like this model B is continuous or uniform in some sense. Because if you look here at this clause here, just say, okay, T has a model B such that B is Turing computable from X. Yeah, okay, but I mean, I would guess that not only does T have a model B such that B is Turing computable from X, but rather there is one specific Turing operator which gives you this model, no matter what X you have here. Like there's always one index that produces this model. And that's actually the case, but that's something that you need to check because it's not mentioned in the theorem. Yes. So once you have all of this, you actually get like these reductions. So you get that if you don't have a bounded, you have a bounded quantifier, you have no bounded quantifier axiomatization if and only if the set of models is pi omega complete. Which was quite surprising to me. And as a corollary, you get what I was interested in the beginning. You get, well, if you look at the models, say of Peano arithmetic, the set of models of Peano arithmetic, or the models of T for any completion of Peano arithmetic, then you get that those are also pi omega complete, in particular true arithmetic. And why is that the case? Well, it's just basically follows directly from Tarski's undefinability of truth theorem and the existence of partial truth predicates. Well, if there was, because like if there was a bounded axiomatization, then there's like a partial truth predicate somewhere, which is going to tell you, whether a formula is true or not for any formula, because you have a bounded axiomatization. And then that contradicts Tarski's undefinability of truth. And I mean, for PA, it's very easy to produce like this theories Tn. You can just break sigma n induction or sigma n minus 1 induction at Tn, something like this. Okay, so fine, we have this theorem, and we were thinking, okay, we have like this general theorem, and we know we can prove ourselves, okay, that basically completions of PA have a very complicated set of models. But are there any other theories that have this behavior? In particular, what happens if you take PA and you drop all induction axioms? then you end up with the theory which is called PA minus. So PA minus is just the theory of all of the discrete semi-ring. It doesn't have any induction. And we were thinking, well, probably our theorem needs a lot of induction. Like probably if you drop the induction, then this won't work. There are like completions with bounded quantifier complexity. And we asked Roman Kossak when he visited Vienna a couple of months ago. And Roman said, well, actually, I don't know, but let me ask. And he asked Ali Nayad and Albert Visser. And a couple of days later, Ali Nayad and Albert Visser sent us a draft of a paper where, sorry, I just jumped somewhere here. Yeah, so they sent us a draft of a paper about sequential theories. And let me quickly tell you what a sequential theory is. So a sequential theory T is one that admits a so-called definitional extension to adjunctive set theory. So definitional extension just means like you have the theory T, and within the theory T, you can define a new you can define a new predicate symbol. In this case, because we want to define set theory, the element of symbol that satisfies certain axioms. So it's like a very strong notion of interpretability. Not only can you interpret this adjunctive set theory, but you don't even need to use any quotient or anything. You can do it. You can code the new relation symbols directly. Okay, so what is adjunctive set theory? It's just a very basic set theory that tells you, well, okay, it has two axioms. The empty set exists. And if you have a set X, then you can add a new element to the set. That's all it does. It's very, very weak. And this definition of sequentiality is due to Bakomov and Visser. I think the first one to define it was Putlak in '83, and he actually defined it as a theory which essentially allows for coding of finite sequences. Like if you remember Gödel's incompleteness theorems, he had like these beta functions. He showed that PA allows the coding of finite sequences using his beta function. So essentially, a theory is sequential if you can produce such a beta function as Gödel did. If it can define such a beta function as Gödel did. Okay, so which theories are sequential? Quite a few and quite weak ones are sequential. So first of all, okay, piano arithmetic is sequential. That's basically Gödel's result. But also, if you just take induction for bounded formulas plus exponentiation, that's sequential. I mean, of course, all the set theories like CF or like Kripke-Platek set theory are sequential. But and that is not easy to show. Even PA minus is a sequential theory. So like, if you remember, if you ever taught like Gödel's incompleteness theorems, defining the beta functions usually use induction. But Yarshabek showed that you can actually define the beta function without induction. So also PA minus is a sequential theory. And also adjunctive set theory itself, but interestingly, Robinson's Q, which is a little bit weaker than PA minus, is not a sequential theory. So Nayad and Visser in their paper that they sent us showed that no sequential theory in finite vocabulary has an axiomatization by sentences of bounded quantifier complexity. And the proof basically is also like you very cleverly use like versions of Tarski's undefinability of truth. It's a very nice, clever argument. And I was very surprised by this, that basically our theorem does not rely on induction at all, that even if you drop all the induction, like for every completion, you will have this behavior that you have a pi omega complete set of models. And yeah, just to point out in this theorem, because this holds for any sequential theory, it's important here that the sequential theory is in a finite vocabulary, because otherwise we could just take the moralization, for instance, of true arithmetic, So basically for every formula, add a new relation symbol that basically codes the truth of this formula. And then you can just write the compositional axiomatization of this. And this is just pi2. So this has actually a pi2 axiomatization, and then you lose the completeness. So yeah, as a corollary, combining this with our results, if T is sequential in finite vocabulary, then the set of models of T is pi omega complete. Okay, so this was basically where we were at, I guess, like 2 months ago when I wrote the abstract. But then David and Hongyu came in with some new ideas and said, okay, we should probably also look at what happens with theories that have bounded axiomatizations. What can we say about their complexity of set of models? So this is what we set out to do then. And here again is our main theorem. So if T is a theory and n any natural number, then the following are equivalent. T has a pi n axiomatization, but no pi n-1 axiomatization. And the weight degree of the set of models of T is in the range sigma n minus 1 and pi n. Here note that this interval here contain infinitely many weight degrees as the intersection of those splits into these different degrees. So I guess just as a reminder, right? Like you have here sigma n, you have here pi n, they're incomparable. And then you have here like this huge blob, which are the delta 0 n degrees. And then again, it splits like this. So these are all the possible degrees. And basically what our result basically shows is that like for fear that like kind of like these are like, you can have stuff in this range. Well, I mean, okay, I mean, this is nice. I was, of course, hoping for something a little bit better to have like, I don't know, if you have a pi n axiomatization and no pi n minus 1 axiomatization, if and only if you have like degree pi n. However, unfortunately, this doesn't hold. And the problem is if you look at theories which have like sigma n axiomatization, because they can have basically like weight degree sigma n, so they can, if we translate it down one level, they can lay around here, they can lay up there, and they can lay also like somewhere in here in the difference hierarchy. We only have an example so far for D2, but at least for the finite levels of the difference hierarchy, we can produce examples. Okay, interestingly, you don't get the weight degree sigma 2, so this should be boldface here, because we were able to show that there is no complete consistent first order theory T, such that the set of models of T is sigma 2. Sorry, you don't get sigma 2 for complete theories, of course. For non-complete theories, you get it. And what is the reason? And the reason, like I guess that's most understandably for a computability theorist is, well, we all know a sigma 2 set of natural numbers that's complete, namely the set of the set of indices for finite C sets. And the reason is quite similar. If you look at the set of strings that only have finitely many ones, that's a sigma 2 complete set in the Borel hierarchy. And so basically what this tells you is that a sigma 2 infinitary sentence cannot express that a structure is infinite. I mean, that's the overarching reason. So if you write down any sigma 2 sentence, then the sigma 2 sentence must have finite models. Well, but if the theory is complete, then essentially the mod T is going to be empty because it's only going to have one model, namely the one finite model, and this one finite model is not in this Polish space. Okay, so how do you prove this theorem? Like this other main theorem of us for bounded? Well, it's quite similar. You have to again use like this kind of lemma that lets you produce like this weight reduction F, such that if Fx is in a set of models of one theory, So, okay, sorry. So say you have two theories, T plus and T minus, such that the sigma n fragment of T minus is a sigma n fragment of T plus. Then we can produce a weight reduction F for any sigma n set, such that F of small x is in mod T plus if x is in x, and Fx is in mod T minus otherwise. So mod T plus is sigma n hard, and mod T minus is pi n hard. Notice here that there's like, in the case of pi omega, we had to produce in the sigma outcome infinitely many different theories. Here we only need one. But the proof of this is basically very similar to the proof of the unbounded case. Like, essentially, yeah, it's basically this almost the same proof. Just that basically at some finite level you branch off and then you stop branching off and you produce either one or the other. So that's why you only need two theories. The other lemma that lets us deal especially with like incomplete theories is essentially follows from a compactness argument. Sorry. Let A be a set of first order sentences and phi a first order sentence such that A does not prove that phi is equal to psi for any pi n sentence psi. Well, then you can take two complete consistent theories, one theory that contains A and makes phi true, and another theory that does not contain phi, but the sigma n fragment of T minus is contained in the sigma n fragment of T plus. So that just like lets you basically get such theories from an incomplete set of sentences for this lemma up here. And I think I have like a couple of minutes, so I can just quickly go over this compactness argument because I find it very cute. So it's basically two claims. So first, the theory A union phi union the sigma n theory of A union not phi is consistent. Well, suppose it is inconsistent. Well, okay, then by compactness, you can find a single formula psi in the sigma n theory of A union not phi, such that A union phi proves not phi. Okay, but then A proves phi is equivalent to not phi. But psi was a pi n formula, and we assumed from the beginning that phi is not equivalent to a pi n formula, at least not provably from A. So we get a contradiction. And we can then just use any completion of this set as our T plus. So having this T plus, we now claim that the pi n theory of T plus union not phi is consistent. Well, suppose not. Well, what happens then? Then there is a psi in the pi n theory of T plus, such that psi proves phi. Why is that? Because of course, this guy itself is consistent. So we have that psi proves phi, and hence not phi proves not psi, just contraposition. But then not psi is in the sigma n theory of A union not phi. And the sigma n theory of A union not phi is a subset of T plus. So T plus itself cannot be consistent. And this allows us to choose like some T minus that satisfies the conditions of the lemma we need. Okay, so this concerns this main theorem. So we have like, as a takeaway point, we have like this nice characterization of a theory of the array complexity of a set of models in terms of the first order theories quantify complexity. We also get the theorem that Kiesler proved in 1965 again. If a finitary first order formula phi is equivalent to psi to an infinitary pi n formula, then there is a pi n formula theta such that phi is equivalent to theta. So this is just basically using our theorem for the finite case with a single formula, phi. And our proof only works for L omega 1 omega. Kiesler's proof worked for L infinity omega. However, and this is something for the future, I have not really studied it yet, but Kiesler's proof seems to use games. So he used games. So I'm quite certain that Kiesler's proof needs at least like arithmetic determinacy or something like this. So like determinacy for pi omega sets. And Harrison, Trainer, and Kretschmann used forcing with elementary extensions. So there's also like some sort of meta-mathematical flavor here. Well, our proof doesn't, I mean, it's combinatorially hard because you use like these iterated priority constructions, but it doesn't rely on any big axioms. And in fact, we conjecture that our proof should be equivalent to WKL naught, and thus really should, so really the fact that this holds should really be just a compactness property, which I find very nice. Yeah, but that's still a little bit in the future. That's not going to be in the paper we publish. We hope to put on the archive this week. Okay, thank you very much. This is all I had to tell you.
Okay. Thank you, Dino. Thanks for the speakers. Any question?
I have a question. Can I ask?
Yes.
Could you, yeah, thank you. Dina, could you please show the previous slide? Yes. When you are talking about equivalence to Wittgenstein lemma, how do you formalize infinitary formulas within the reverse mathematics? How do you do this?
Yeah, so I mean, that's I mean in the end basically using codes or real codes, like just a tree, right? Like a well-founded tree. So like if you have a pi omega formula, then the rank of the well-founded tree is quite low. So that should allow you to formalize this in reverse mathematics. I mean, as I say, like this is quite raw. I mean, I haven't even, I guess, like thought too deeply about like the formalization part of this. Just like I mean, we just looked at this and we're like, oh wait, this is all this is using is somehow compactness. Like,
Thank you.
Okay. Any other question from audience? Okay, so there looks like no questions. Thanks again for the speakers. Thank you, Dino.
thank you.
Yeah, that's it. So thanks again for today's all the speakers.